Hi, my name is Vahan Davudian. I'm a physics experimentalist for 30 years. And then, first of all, I'd like to thank so many viewers. They emailed me, and then they just appreciated what I'm doing. That is so rewarding, and that's a good feedback. Thanks a lot. And today is so special because not only I have some posters, but also I have some very important experiment, and it's about the cycloid or Tautochrone. It's a very simple device, but it's you know, it's mind-blowing thing because it's so not easy to understand. It's got so much physics on it. So anyway, I embark on a quest to shed light because I'm not a nosy person, but I had to check the YouTube. I saw almost like more than 25 theories. Very educated people, they did that. They did explain how you could do the cycloid, and then you roll a circle on a straight line, and then, well, it was okay. But you know what, it is blowing for me that some people watched, some of them are like, it's just a history. After 33 years, I can talk about the science history all day long. It's just easy. How could 7.5 million people watch that? I cannot understand this, beyond my imagination. But anyway, I said, Vahan, you have to solve this problem. Almost all of them, they have a picture, and then they show that, cyclotron, the rolling is getting much faster. Well, of course, there's a lot of physics behind it. They gave us formula, pi, and so many things. That is not going to help for the viewers. Viewers need to know what is the logical analysis of it. How does it work? But let me show you one. 90% of them, so they have, like a weird one like this one, and this is the cycloid or tautochrone, and this is Galileo's ramp. And well, of course, it's obvious this one is going to get there much faster. People are not interested in the picture. They want experiment. And as a matter of fact, I have 4 experiments. They're extremely important. You are going to be amazed after you watch that, because most of the time I can see even Mythbusters, they were good, but they had wooden ramp. It's not real. Precisely the way I do, because I had to use the special ramps, which is plastic, and they're so sharp and the friction is so less. And guess what? I did 2 ramps side by side, so I can roll 2 balls at the same time, so you can tell which one is getting later or which one is getting much faster. So anyway, in order for you guys to understand this, because like I said, it's a little bit difficult, but I have to take you 400 years ago so you can find out exactly, you can connect the dots. What do we mean by cycloid? Well, it started with Galileo. All this pendulum, cycloid, tautochrone, everything is connected. So it's equal areas, equal times, and especially pendulum. And guess what? Cycloid is practically inverted, pendulum is practically inverted cycloid. So I had to overlap that, and I incorporated so you can tell how easy it is to understand. Well, first of all, I like to talk about the Galileo, and he was amazing scientist. And in fact, if you want to watch my videos, I had this, I think, let me double check again. It was 2 years ago. It was theory of falling object, and then I explained about the Galileo's real good. It's 1.5 hour. Also for the pendulum, like a year and a half ago, I did when I came back from France, and that was amazing. That was a good success, so you can also watch that. But before that, I have to let you know what Galileo did, and then what do I mean? I replicated most scientists' experiment. And this is the one for Galileo's ramp, so you can see this is called a ramp, and you can see it's a straight line. But something amazing about this is that Galileo discovered that, see, this one position is different, that one is different, that one is different. So he came up with this formula which was amazing. I mean, he just set the stage for Sir Isaac Newton and everyone else, and that was called Galileo's uniformly accelerated motion, and he came up with this formula. Distance traveled is equal to half of the acceleration multiplied by times squared. And in fact, I had to compare this with Christian Huygens, cycloid, because you can tell. Here you can see he has a ramp over here. Galileo's ramp was exactly like this, but what I did in year 2000, I had to bend his ramp. Well, of course, I show you in my experiment. So I had to add another ramp over here. So in other words, I had to make exactly like a V shape. So why did I do that? Because when Galileo was alive, there was no idea, they had no idea about the kinetic energy or things like that. But he was genius, he figured it out. So what happened, I added another one here, so when the ball rolls over here, I can tell how much kinetic energy it, gains, and then how much it propels to the opposite. Okay, so, but I have to explain what do we mean by half of acceleration times 2. So, see, this ramp is almost 133 centimeter height, and then I did this by year 2000 with great precision, and I remember I must have worked on this maybe 4 or 5 months, and the acceleration on this is exactly 1 meter. 1 meter per second square is 10 times smaller than free falling object. Imagine here the ball. So one more thing is important. I didn't mention that. So he also discovered, Galileo, that velocity is acceleration multiplied by time. So here we have velocity and we have acceleration. Velocity is so important because it shows the direction and it also shows the magnitude. So you can say here, the ball travels in 1 second, exactly 50 centimeter. So you can tell it's 1 meter per second. And then in 2 seconds we have velocity 2 meter per second, and 3 seconds we have 3 meter per second all the way. But you see something amazing happened here. So here we have, the ball travels 2 meters, right? So 2 times 2 is going to be 4, times 0.5 is going to be exactly 2 meters. But here, ball travels, see, here, you can see, travels 3 seconds. So what happened? 3 times 3 multiplied by 3 is going to be 9. 9 times half is going to be exactly 4.5 meters. But here's the amazing thing. Here ball travels exactly 4 seconds. This is so important. Please listen. So 4 seconds. 4 times 4, which is the square, that'll be 16. So 16 multiplied by 0.5 is going to be 8. So you can see the ball travels in 4 seconds, in 4 seconds, 8 meters. That is spectacular. So this is the way he did, and this is his ramp. In fact, this is the original. But he was genius. He put some bells over here, so every time the ball rolls here, but you can see this distance is small and getting larger, larger, larger. So Galileo discovered that ball is rolling down the ramp is not going to be the same, and then he came up with this formulas, which was groundbreaking. It was breakthrough at that science, and in fact he set the stage for the Sir Isaac Newton, because he discovered the first laws of motion, and then Sir Isaac Newton was also genius. He came over and did the second and third law of motion. But overall, Galileo was the one, and then later I tell you everything happened in a church, because he inspired from the pendulum. Okay, now let's talk about this Tautochrone, which is for today we're talking about this. Sometimes they call it cycloid, but this is the one I'm going to work on this today. Tautochrone analyzed and explained conclusive, I'm sorry, with unprecedented precision by Vahan Davudyan, physics experimentalist, and this is my email, vahandavudyan1948 @gmail.com. And this is the cycloid, you can tell, and this is amazing device. And then I have to criticize some people who did this on YouTube. Nobody mentioned Christian Huygens. He was the one who finished this. He was the one who started this, and in fact, he was the one. He worked on this cycloid, to make a better clock, because as you remember, he invented the pendulum clock. So you can see we have cycloid over here, but I had to do exactly the way I did it with Galileo. So I had to add another cycloid exactly like this, so make it 180 degrees. Why did I do this? So you can see here I have A, B, C, D, E, F. So my cycloid is exactly 90 centimeters, and I did this with fantastic, great precision. Each one of them is exactly 15 centimeters, and then I did it with centimeters, because I could even check the millimeters also. So you can see this is one cycloid and this is another one. So why do I have this one over here? The reason why, you can see here, I have kinetic energy. So this part, I can tell how much that ball is getting kinetic energy. And the most important part is I had to calculate with a great precision velocity. And imagine the number A, which is on top, has more potential energy. Velocity is 1.8 meter per second. Number B, which is 15 centimeters less, is velocity is 1.5 meter per second, and then second one, third one comes 1.2. And imagine this number A has more kinetic energy, and then it travels more. So in order to substantiate my ideas for the kinetic energy, I had to roll these balls all the way to the opposite, cycloid. And imagine this A, which is pink, can go 70. That is incredible, goes to 80 centimeters. Like this one goes only maybe 25. But like I said, this is the idea I came up with, because unfortunately, none of these theories on YouTube, they mentioned this. And this amazing. This kinetic energy is so important. Let me explain a little bit. So this is the formula, but of course on my next poster I have to explain who came up with this idea. Kinetic energy is half of the mass by velocity squared. But something amazing about this formula, you can tell, if your mass is 100 grams, you have to divide it by 2. Then if your mass is increased here by 2, if your mass is 100, you increase it to 2, so your kinetic energy is going to be double. But something amazing is here. If your velocity is doubled, your kinetic energy is going to be 4 times more, see, because V is squared. That is so amazing. I mean, this formula is so important, and this kinetic energy is I can see I used all of them like this. So you can tell how important it is, to inspire from the, people like Galileo and the others. Now I have to get another poster so you can see who discovered this kinetic energy. This was the genius Miss Amélie du Châtelet from France, and she was an amazing person. She did not have college education, but at those days, 300 years ago, because she was contemporary with Sir Isaac Newton and then Christian Huygens and all those scientists. Those days, education did not mean anything for the girls or for the females anyway. But she did it, and she was from a wealthy family, but she did it. Well, these are the Galileo's ramps. And practically we owe it to him because he started this. So we have the low incline and we have the high incline. And he was so genius to figure it out. It doesn't matter if you use either one of these ramps, this proportion is not going to change. Those days, there was no ramp those days. So Galileo came up with this idea. I bring it a little bit closer, you can see. There was no clock, there was no watch. So Galileo came up with this idea, he called them notch. So after one notch, see what happened, ball travels almost like the way I said, 50 centimeters. After two notches, traveled more. Three notches more, and after after three notches, this ball travels 9 lines. So he did it that way. But everything started in a church. This is called Pisa Cathedral, and then I don't know why he was in medical school 2 years, but this changed his life. He was watching, the monk came, and then, of course, this is not the actual one because this is electric, but this is the actual one, which I couldn't find a good picture. This was so huge. It's a bronze. And then the monk came over, pulled the chandelier, because those days, 400 years ago, there was no electricity, to light the candle, and then let it go. Galileo was in church at the same time. He realized the pendulum is going back and forth, is swinging. But I don't know where that genius thing came from that, he had to use his pulse. Why? Because he was in medical school 2 years. He was one of the greatest minds in the history of mankind. So he used his pulse. He realized the small arc for the pendulum, it was a huge pendulum. I have no idea how much it weighs, but I'm guessing, see how high it is. I'm guessing this must have an arc, a huge arc and the small arcs. And then he checked with his pendulum. He realized a small arc is exactly the same pulse, and the big arc is exactly the same. He had to rush home. He said, I'm not going to continue being a doctor. I want to be a physicist. So he discovered this. So anyway, he went home. Then after, many years after that, she took over. But there is a fantastic story for Amélie du Châtelet, because she was amazing scientist. I have never seen such a talent in my life. And later I will explain why her formula is so close to Albert Einstein's formula. Well, of course, I'm not suggesting or I'm not implying it's the same thing, or he inspired from her, or it was plagiarism or anything. But it's a shocking discovery. So is E is equal mc square. This is velocity, and that one is celero. But of course, I have to be fair. She had no idea about the mass. She had no idea about the energy and things like that. She didn't have college education like, Albert Einstein. But imagine all these formulas, they are connected each other. So this is what happened with her. She was so genius, and then she translated so many books, and she was studying every day. So what happened? The first husband was in army, always traveling, but the second husband was so good, and then his name was Voltaire, and he was also philosopher and also scientist. But unfortunately, he had a problem with French government, always, in the run. And then one day he was in Netherlands, in Holland. Then he realized they're doing some experiment, and despite the public perception, people were thinking if you drop a ball in a clay, if you increase the velocity from 1 to 2, it penetrates 2 times. And the Voltaire noticed, no, it's the opposite. It's the 4 times. So immediately he wrote a letter to his wife, and Amélie was so good. Her mind was prepared. Now I have to take you back to Louis Pasteur. One time he said, the chance only favors prepared mind. Her mind was prepared. And guess what? She had no college education. She argued with Sir Isaac Newton. Sir Isaac Newton said, my formula is E is equal to mv. He said, no. E is equal to mv squared. I mean, how could you argue with Sir Isaac Newton, one of the greatest minds in history? But she did it because, she was right. So when Voltaire wrote that letter, and then she did some experiment with pendulum and everything else, she realized nature, everything is multiplied by itself, squared. Well, anyway, she came up with this formula. Well, of course, I have to tell you something important. This is a constant. This was not there at that time. It was added later, but I have no idea who did this. So, this experiment in a Dutch physicist, his name was Willem Gravesande, and what he did, he dropped brass balls in a clay. I did the same experiment in a flower, and then I realized flower is much easier because I can see the penetration is a little bit softer, but clay is a little bit harder anyway. So I did it, and then I realized, Willem was right, 100% right. When you increase the velocity by 2, it travels 4 times. It's a square. So this is what happened, and then I really, concluded that everything is a square, and this was one of the greatest discoveries in mankind, and still we enjoy this. And unfortunately, what happened? She was only 44 years old, and then for the second or third child, I'm not sure, she passed away. Always, I took Albert Einstein like a, role model because he was an amazing person. And you know what? He was connecting all the dots. I don't know why. I call him Mr. Synapse because in a human brain there's a synapse. It's it can connecting billions of neurons together. Albert Einstein was a nosy person. He was amazing, a sneaky person, but at the same time he was smart. He was getting all the input from the people and analyzing, come up with his own ideas. And I said, Vahan, you do the same thing. You have to connect the dots. But how Vahan can connect the dots? I said, I can do it. So what I did, I had to incorporate pendulum in the cycloid. You can see a few minutes ago I mentioned that, this is one cycloid, this is another one, and then this is my pendulum. Practically, this is inverted cycloid. And then you can see this, purple ones or the black one is the pendulum, and this is the one which I mentioned a few minutes ago. And like I said, this one had 1.8 meter per second velocity, but that one has 1.5 meter velocity, 1.2. And imagine when I put this together, they match perfectly. I mean, isn't this amazing? I mean, the pendulum and the cycloid, they match perfectly because that's exactly what happened. This is acceleration due to gravity, and everything is the same. So imagine those sections, they match perfectly. This is the cycloid, and this blue ones, or this matches perfectly with those. Imagine. So this is the way you can see why the laws of physics are always connected. And I did not say something. It doesn't matter when you release the ball on the cycloid, it doesn't matter. But I show you in my experiment, from here or here, it takes exactly, because my cycloid was exactly, I did it for maybe, I got my stopwatch maybe for 100 times. This is my stopwatch, maybe more than 100 times. And then I realized it's only 0.5 or 0.5 second. Well, when I did Galileo's ramp, I have it over here, I show you, it took 0.6. So imagine, the cycloid is always faster due to having this fantastic velocity and at the same time gained kinetic energy. Kepler was one of the amazing physicists, astronomer in the history. Well, of course, he had to work with Tycho Brahe. He was an amazing person, but he did not want to give any information when he passed away, and then Kepler took over. And he's so famous for his planetary laws. And then it was year 2000, and then I was having a speech in Regis University, DeVry University, and the others. So I came up with this idea, and unfortunately there were some scientists, physicists, astronomers, they were so jealous, and then they knew that, I don't have a PhD. They did not want to acknowledge this, but, later on, I heard that they did acknowledge, but they don't want to cooperate with me. So this is the planetary law for the Kepler. Kepler was an amazing physicist. He found out that, there's a sun which is not in focus. Then this is called perihelion and aphelion. Well, I'm not sure if I'm pronouncing them right because they're Greek word anyway. So he said, if there is a line stretching from the sun to the planet, they get equal areas, equal time. So you see, this is a little bit larger and this is a smaller. This is exactly what happened in a pendulum. So I have a big arc over here, I have a small arc over here. This is isochronism. What happened? Pendulum finishes exactly the same time. So imagine the planets are the same way. I mean, isn't this everything connected together? So no one has done this before. This experiment I'm going to show you in a few minutes. No one in history has done this before. And like I said, unfortunately, I didn't see any cooperation for those scientists. And then this is amazing. So if you compare pendulum with those planetary laws, they're the same. Most of people pay a lot of money, to, computer geeks to get them, like a thumbnail, but I created my own. This was my imagination. So I had Bart Simpson and Homer Simpson. I think this one is Bart Simpson and Homer Simpson. So I had to manipulate I had to cut the head here and put Galileo's head, and I had to cut the head over here and put Christian Huygens' head. But imagine how easy it is to understand that, what the Tautochrone is and what the Galileo's ramp is. Because practically these straight lines, nobody even mentioned this Galileo's ramp. They just show us, some people, display that on YouTube. But this is the straight one is also called Galileo's. And then you can see this is finishing this. So this is Christian Huygens, and they are in skateboarding, and then these are the balls, and no matter, like I said, wherever you release this, they're going to get the same place. So Tautochrone analyzed and explained conclusive with unprecedented precision by Vahan Davudyan. And I love this part. They say, hey Christian, you beat me. No Galileo, it is laws of physics. These are my ramps, but 1 second, I'll be right back. You can see this is my ramp, and exactly the way I did it on the picture, you can see I have A, I have B, I have C, D, E, F. And then each one I mentioned, let me get out of the way, you can see here. See, like this one on top is 1.8 meter per second, and the second one, which is B, is exactly 1.5 meter, and the third one 1.2. So this is the velocity. So what it is, the velocity is amazing. I mean, this is the only way you can see what happened. But here is amazing thing, I had to get another one here. It's a Galileo's ramp, and you can see this is like a V shape, but this is exactly two Tautochrone back to back. But let me roll the balls over here. You can see what I mean. See, this is Galileo's ramp. This is exactly the same height, and this is Tautochrone. Let me roll the ball. You can see which one gets faster. You see what happened here? As they go the opposite side, it's a gained kinetic energy. But no matter how you do it, Galileo's ramp always, finishes after this. So this is amazing. And like I said, velocity is so important. But I have to show you something. Most people on YouTube, they show that, they have a circle like this. So they roll the circle like this, and then they make a Tautochrone, or they make a cycloid. That was good idea. I like it. See? If you mark on a roller like that, that is going to show. I have to show something else. This was my invention. I came up with this idea. See, this is not only a vector, but also is a tensor. So what it is, if I have it over here, let me show you. If I have a ball over here, look. See, this is accelerating toward the center of the earth. See this ball? So what happened? All these, they're in one line. Well, what if I bring the ball over here and then, see, this is going to be a little bit different. Now we can have an angle over here. See, I have a protractor over here, see? Now I have like 55 degrees here. See, I bring it up. So the smaller the angle, the more acceleration get. And this is so good. I remember I displayed this in a religious university, and people would understand why the ball is rolling. See, right here. Why? This is why. So you have the weight or gravity, you have acceleration, you have the net force, and you have also support from the ramp. Well, of course, this is pushing on the ramp, and the ramp is pushing on Earth, because if I'm like 72 kilograms, Earth is pushing on my body 72 kilograms. That's why I'm not falling. I also came up with this fantastic idea that I had to invent this idea. Let me put this over here. This is a laser beam. Why did I do this? Because, you know, sometimes people, it just happens so fast, they won't be able to see why things are happening so fast. I have to put this laser. So every time this ball is, this is the center line, is blocking the line, you know, blocking the laser beam, you can tell. Okay, let me turn this on, please. You can see, whenever it's passing the laser beam, what happened? See, you can see the flash. But something amazing happened. If I have it here, which is the lowest, and then I put another one on top like this, they, you know, finish at the same time. So you see, I have this laser beam over here. So whenever you see that, did you see that flash? So every time the ball is going through the center line, it's just finish it. But this is important. Why did I use these three lines? This is so easy for, you know, viewers to understand why the ball is getting faster. So I have a smaller here, which is number F, and I put the other one all the way on top. Did you see? That was amazing. Did you see how fast it is going? But I have to mention something. You can see here on top, this is almost like a free fall. See how steep it is? But the Galileo's ramp is just gradual. So it doesn't matter when I release this. Let me show you one more time. If I have one over here and then one over here, you see, check this one, see how fast. But you know what? The important thing is it also substantiates my idea. See how far that goes? But this one goes, it's not going that far. The reason why, the velocity was less. At the same time, the gained kinetic energy on the opposite side was less. Let me show you one more thing. So, you know, like here and there. Do you see how far that goes? It's because of gained kinetic energy. And it doesn't matter. I can, you know, have one over here, one from there. They exactly coincide at the same place, you know. I had to use this because these are plastic and the precision is 100%. You can tell how good they travel. Look. And it is impossible, you know, these are the best, rollers, you know. I've got these mulberries, they're the best. I can even use the big ones like this, eh? That's the cue ball from the billiards. Yeah, I can use this also. See? This is amazing. I mentioned this by year 2000. You can watch my theories for the theory of free falling. I have 28 grams and 56 grams. This was, so good. This was, breakthrough in science. If I have this on a lower velocity like this, and then this one has in a higher velocity. So what happened? They both finish at the same time. Look. So what happened? Mass becomes acceleration and the acceleration becomes mass. See how easy it is to see the balls, you know, the bowling balls finish at the same time. The reason why you have this laser beam and then you have two ramps, so you can tell how easy it is. These are a little bit smaller, you can tell, see? It doesn't matter. I release this from here, I release this one from here, it doesn't matter. Look, see? But it's amazing when it releases from the top. I mean, the velocity is so good, so that's why it compensates. I have to get this laser and then show you something else. See, if I have a pendulum like this here, if you remember a few minutes ago I said it's an inverted pendulum. Pendulum goes exactly like that, see? Exactly the same portion. Equal times, equal area, see? But I have to show you the real pendulum, which I have it over here. Let me put the pendulum so you can see. Okay. So pendulum is an amazing device, and like I said, I had to incorporate this. You can see this part is called equilibrium. So in other words, it's going toward the center of the earth. When I do it like this, I'm displacing. So it doesn't matter how much I displace this. See, pendulum 1, 2, 3, 4, 5, 6, 7, it doesn't matter. The restoring force is the gravity force. It's exactly proportional. See, if I displace this by 2, it's going to go back to the same. And it doesn't matter. If I take the time, well, of course, you won't see it on my watch because it's too small. You can see. I did it with my, stopwatch. It's exactly the same. Well, of course, I have to mention something. This is for small arcs, which is good for our purpose. You can see 180. And, you know, if I do it from the top, it's going to be the same. Did you see what happened here? The velocity is so good. But see, if I do it from here, you can tell. You don't have to be genius to figure it out. Did you see how small it is? How slow it is? But from here, that restoring force is amazing. So I'm glad, you know, I had to incorporate everything together. But, you know, I would appreciate if you guys take this into the consideration and compare with the others. And then I'm not saying 1 million people will watch it, but this was so comprehensive, and I'm sure, you know, I shed light on this, and I'm hoping you guys would love it. And then I appreciate your feedback. And then if you have any question or concern, you can email me. Thanks a lot for watching this video, and you know, I did cover, I think, everything, and you know, I'm glad I have a fantastic viewers like you, because you guys are always inspiring for me. Your ideas, your suggestions, I always take everything into the consideration. Thanks a lot for watching. Bye bye.